So in this example, we have a trig integral, and I'm going to be using integration by parts. It's the integral of t times sine of t times cosine of t dt. And why integration by parts? Why would I choose to do that? Well, looking at this extra t in front is what's making me think integration by parts. If I try to do any u substitution, like I've done previously where I let u equal sine of t, and then I get a cosine t, this extra t in front is causing some issues. And so that's what makes me think, well, there's a product going on there I kind of want to break up. So I think integration by parts. So I'm going to go ahead and set that up. And how you set up your integration by parts, I know there's a bunch of strategies and I get better and better at it each time I do it. But honestly, I kind of go through a certain couple scenarios, try it out, and then I end up with what I choose for my pieces of my integration by parts. So after some thought, I ended up with u equals t. And so du equals dt. And dv, I let, of course, that be sine of t, cosine of t, dt. And then v, what's that going to be? So I actually went off to the side, did a little scratch work here and said, well, I need to find the antiderivative of sine of t, cosine of t, dt. So I got to find this antiderivative. So if I let u equal sine of t, because then my du will come out positive. If I let it be cosine of t, I'd get a negative sine of t for du, and I wanted positive. So I have a cosine t dt for my du. That would give me the integral of u du, which is u squared over 2 for the antiderivative, and then plugging back in my substitution, I get sine squared t over 2. So a little scratch work on the side gave me my v of sine squared 2 over 2. And now I can do my integration by parts formula. I have uv, so t times sine squared t all over 2. And that's going to be minus v du, so minus sine squared t all over 2 dt. And then looking at that, I did integration by parts, but now looking at the sine squared t, I go, okay, I've got a trig integral I got to deal with here. So I'm going to ignore the t sine squared t for a moment and just deal with this integral I have here. Now, this integral of sine squared t, well, actually, I'll rewrite all of this. So t sine squared t, that's all over 2, minus, I'm going to pull out that 1/2. So sine squared t over 2 is just 1/2 times that. So I have 1/2 the integral of sine squared t dt. And now I'm going to deal with this sine squared t off on the right with a little scratch work. So sine squared t, that if I use my formulas that I have for my trig integrals, I'm going to go back to one of those identities. So these formulas are everywhere, but I happen to have them in this nice one spot here. So I have sine squared x equals 1/2 times 1 minus cosine 2x. So I'm going to bring that into play here. And I'm going to distribute that 1/2. So I'm going to write it as sine squared x equals 1/2 minus 1/2 cosine, or sine squared t equals 1/2 minus 1/2 cosine 2t. And that's now going to be something I'm going to find the integral of. And so if I were to find the integral of that, that would actually be the integral of 1/2 dt minus 1/2 integral cosine of 2t dt. And then when I find the antiderivatives, I get 1/2 t minus 1/2, and you could do another u sub to try and figure this out, but I've done enough of them. I go, okay, that cosine 2t, when I find the antiderivative, I'm going to get another 1/2 popping out, and then I have a sine of 2t. So the antiderivative of cosine 2t is 1/2 sine 2t. So now I can replace that with this integral of sine squared t. So this becomes t sine squared t all over 2 minus 1/2 times the entire quantity of 1/2 t minus 1/4 sine 2t. And then I'll deal with my plus c in a moment. And just going to do a little distributing here and changing of the signs. So I get t sine squared t all over 2 minus 1/4 t plus 1/8 sine of 2t, and then of course that's a plus c. And there's my answer. So this used integration by parts and trig integrals. So two of the strategies for were utilized to solve this integral.